So there it is, sitting right there in a jewelry case, in a pencil cup, in the soot on a burnt piece of toast. One single atom showing up in 100 different disguises. And here's the thing, one of those disguises almost didn't exist. There was a version of the universe where this atom never got made, and none of us would be standing here at all. But that's not even the twist. That's just where our story begins. Yo, what's up? Today, we're talking about carbon. And look, I know carbon sounds like the word that put you to sleep in 9th grade chemistry, but hang with me, because here's the deal. By the end of this, you're going to know why the entire universe almost skipped carbon completely. You're going to find out that outer space is missing a giant pile of it, like somebody robbed the cosmos and left 0 fingerprints. And you're going to hear about diamonds that come from so deep inside the Earth that scientists still argue about how they even got back up to the surface. And here's the kicker. The last mystery isn't in some faraway galaxy. It might end up glowing in your hospital room one day. Let's get into it. Okay, so first thing you gotta understand, carbon is basically the connector atom. It links up with almost anything, which is exactly why it can build DNA, muscle, pencils, diamonds, all of it. But before carbon could build anything, it first had to exist, and that's mystery number 1. Picture the inside of a star. Insanely hot, insanely dense. Helium nuclei, those are the little dense cores of helium atoms, smashing into each other constantly. Slam 2 of them together and you get beryllium. But here's the problem. That beryllium is garbage. It falls apart almost instantly, way faster than a 3rd helium nucleus can come crash into it. So on paper, carbon should barely exist anywhere in the universe. But hold up, this is where it gets messy, because obviously carbon does exist. You're made of it right now. So something's not adding up. In the early 1950s, a British astronomer named Fred Hoyle looked at this problem and basically said, wait a second, I'm made of carbon and so is everything else, so there has to be a cheat code here. He predicted that the carbon nucleus must have a hidden excited state, a temporary high-energy shape with an energy level that lines up almost perfectly with beryllium plus 1 more helium nucleus, like a slingshot, timed exactly right, letting that 3rd helium nucleus sneak in before the beryllium falls apart. And nobody had ever seen this state. It wasn't in any textbook. It wasn't in any experiment. Hoyle just called it, based on the fact that we exist. So he badgers a bunch of nuclear physicists into actually running the experiment, and they find it, exactly where he said it'd be, down to the number. It's called the Hoyle state now, and it's one of the most famous predictions in the history of physics. Okay, but real quick, let me ask you something. Doesn't that feel a little too convenient? Like the universe just happened to be tuned exactly right so that carbon, and therefore us, could exist? Here's the actual mystery, and it's still unsolved. That Hoyle state only lines up because of how strong the nuclear force is. If that force were off by less than 1%, stronger or weaker, the whole slingshot misses. Carbon becomes vanishingly rare. No carbon, no organic chemistry, no life, nothing. So why are the forces of the universe tuned so precisely? Nobody knows. It's one of the biggest open why questions in all of science, and it's mystery number 1, sitting there unsolved since the 1950s. But here's where it gets even weirder, because it turns out, even after carbon gets made, a huge chunk of it goes missing. Look up at the night sky sometime, and you'll see these dark patches that look totally empty. They're not. They're massive clouds of gas and dust, the raw ingredients for future stars and planets. And when astronomers study the light passing through those clouds, they can basically fingerprint every element that's in there. They find plenty of oxygen, plenty of silicon, but carbon? In cloud after cloud, they're only finding about half of what the math says should be there. Half, just gone. Scientists actually call this the carbon crisis, which, yeah, dramatic name, but it fits, because nobody can fully explain where the other half is hiding. So where'd it go? It didn't disappear. Carbon doesn't just vanish. So somewhere out there, it's hiding in plain sight. One leading idea, it's locked up in these giant soot-like molecules called polycyclic aromatic hydrocarbons. Basically, think of tiny flakes of graphite with hydrogen stuck around the edges, floating through space by the truckload. They're so complex that their light signature spreads out across a huge range of wavelengths, which makes them brutally hard to measure. Another idea, the carbon's tied up in weird non-crystalline nanoparticles that just don't leave the clean fingerprints scientists know how to look for. So basically, the universe is playing hide and seek with its own carbon, and we've been it for the better part of 50 years. But get this, solving where that carbon's hiding is literally the first step in the story of how carbon ends up inside you. Because eventually, some of that dust becomes planets, and once it's on a planet, carbon starts doing something even weirder. Grab a piece of charcoal or scrape some soot off a candle jar. What you're holding is called amorphous carbon, carbon with no neat repeating crystal pattern. Diamonds got this perfect 3D grid. Graphite's got these clean stacked sheets. Amorphous carbon looks totally disordered. But here's the catch. Its properties, how hard it is, how well it conducts electricity, all depend on a hidden atomic arrangement that scientists have been arguing about for over 50 years. There's two camps. Camp 1 says it's a crumpled tangle of tiny twisted graphene ribbons jumbled together like a plate of spaghetti. Camp 2 says no, it's curved sheets with weird 5- and 7-sided rings woven in like little broken pieces of a soccer ball-shaped buckyball. And here's the annoying part. The right answer might actually change depending on how the carbon was made in the first place. So we're literally putting this stuff in lithium batteries, water filters, even artificial heart valves, and we still don't have one universal picture of what it looks like at the atomic scale. Wild, right? All right, you ready for the part where this goes underground? Like actually underground, 600 kilometers underground. Most people think diamonds form about 150-200 kilometers down in the upper mantle, normal diamond depth. But some of the most famous diamonds on Earth, stuff like the Hope Diamond, have tiny trapped mineral grains inside them. And when scientists finally got a good look at those trapped grains, they found bridgmanite and ringwoodite, minerals that can only survive under the insane pressure of the lower mantle, over 660 kilometers down, practically knocking on the door of Earth's metal core. Think about that for a second. A rock you could hold in your hand traveled from a place deeper than we've ever drilled, deeper than we can even send a probe. So there's a deep carbon cycle happening under our feet that we're only just starting to understand. Carbon from the ocean floor gets dragged down into the earth over millions of years. Down in the lower mantle, it melts, reacts, forms carbon-rich fluid, and crystallizes into diamond under crushing pressure. And then, somehow, it has to get back up. It hitches a ride in violent, deep-sourced volcanic eruptions that punch straight through hundreds of kilometers of solid rock and deliver the diamond to the surface mostly in one piece. And here's the part that should genuinely freak you out a little. Scientists think there might be an entire hidden reservoir of carbon buried deep inside our planet, possibly holding as much carbon as every ocean and every drop of fossil fuel on Earth's surface combined. A carbon bank the size of a small ocean, sealed under 600 kilometers of rock, quietly regulating our planet's climate for millions of years, and we will never physically visit it, not with any drill, not with any submarine, not ever. Every single one of those super deep diamonds is basically a message in a bottle from a place humanity is permanently locked out of. Yeah, sit with that for a second. Okay, moving on because it gets weirder. So carbon can hide in space, hide underground. Turns out it can also just flat out refuse to be controlled by scientists in a lab, even today. Picture rolling up a sheet of chicken wire into a perfect little tube, no seams. That's basically a carbon nanotube, but the angle you roll it at, called its chirality, completely changes what the tube does. Roll it one way, it conducts electricity like a metal wire. Roll it another way, it acts like a semiconductor, the exact material that makes computer chips work. In theory, we could build perfect transparent conductors out of one kind and transistors way smaller and faster than silicon out of the other. Here's the kicker though. After literal decades of trying, scientists still cannot grow a batch of these things with all the same chirality. You grow a bunch, you get a random mixed bag. Some metal, some semiconductor, all different sizes and twists, just tossed in together like a grab bag of Halloween candy nobody sorted. You can separate them afterward, but it's slow, expensive, and never perfect. The real mystery is what happens in that split second when a nanotube first caps off and starts growing from a microscopic catalyst particle. Why does it choose one twist over another? Turns out, that moment is insanely sensitive. Temperature, gas flow, the exact shape of the catalysts, and it happens at a scale that's brutally hard to watch happen in real time. But here's why this actually matters to you. Crack this mystery and you basically get a programmable seed that grows an entire forest of identical, perfect nanotubes. That's flexible electronics, space elevator cables, yeah, that's a real proposed use, and next-gen batteries, all unlocked by one breakthrough that still hasn't happened. All right, last mystery, and honestly, it might be the coolest one, because you've probably never even heard of it. Carbon quantum dots. These are tiny particles of carbon, just a few nanometers across. Basically soot so small it starts acting like a molecule instead of a solid. And when you shine ultraviolet light on them, they glow, bright blue, green, red, depending on the batch. And because carbon's non-toxic, unlike a lot of other glowing nanoparticles, these things could light up cancer cells during surgery, build colorful display screens, or sniff out chemicals in the environment. Except scientists don't actually agree on why they glow. 3 competing theories, all still fighting it out. 1, quantum confinement, the particle so small it acts like an artificial atom, energy levels set purely by its size. 2, surface states. Oxygen or nitrogen stuck to the outside creates little defects that trap light energy. 3, it's not really a dot glowing at all. It's tiny individual glowing organic molecules just clinging to a carbon core. And the annoying twist is, it might honestly be all 3, just depending on the recipe, which means every lab's carbon dot sample might secretly be a totally different mixed bag of stuff. So here's where we land. 6 mysteries. A nuclear physicist predicting a particle state that shouldn't have existed just because we're alive to ask the question. Half the carbon in space just gone, hiding in plain sight. A material we've used for a century that we still can't draw the blueprint for. Diamonds that traveled from a vault we will never open. Tubes that flip a coin every single time we try to grow them, and a glow that 3 separate camps of scientists are still fighting over, right now, in labs, this year. 6 mysteries, 1 atom. And here's the thing nobody tells you. The answer to any one of these could rewrite a chapter of physics, medicine, or planetary science, and we still don't have any single one of them fully solved. So next time you pick up a pencil, or look at a diamond ring, or exhale a breath of carbon dioxide into the air, you're touching an atom that helped build a star's biggest coincidence, that space itself can't seem to hold on to, that hides 600 kilometers under your feet, and that, still after 100 years of study, glows for reasons we haven't fully nailed down. Carbon is the great connector between life and non-life, between the Earth's surface and its molten core, between the stars that made us and the dust we came from. And if that blew your mind, wait till you hear what oxygen's been hiding this whole time. That one's coming next.